Hopefully this evening is just a bit of an overview and sort of a bit of a guidance of how to get into it, especially as we can't do face-to-faces at the moment.
Yeah, fantastic. Thank you.
So we've got 10 people said they were interested, but I will kick off at 7:30, so only a few more minutes.
I have forwarded the link to another friend who may join us.
That's okay. Thank you. The more the merrier, as far as I'm concerned.
Well, that's what I thought you'd think. So.
So what I'd like to do is just leave the mics on all the way through, and if the video feed isn't too impaired, leave your videos on as well. The only reason I'd stop that is if someone comes in and starts Zoom bombing us. So I'll leave it open until we're forced to have plan B. Has anyone been in a Zoom bombing session?
No.
No, what happens? It sounds very exciting.
Zoom is a great tool, but it assumes that everyone's nice.
Okay.
And so everything's switched on by default. So if you just start a session, then anyone can start writing on your screen or sharing their own screen. And you actually have to know to switch those things off.
Right.
And there's no real guidance about switching those things off. So people fire up a Zoom session, then which one? It was the Virtual Astronomy Club got Zoom bombed last week, which wasn't particularly nice for the poor speaker.
No.
The way they've designed it is only the person who's actually sharing their screen can switch off the problem. So they had a speaker who didn't know anything about Zoom other than just using it as a participant. So yeah.
Oh dear.
It was an oh dear moment, yes. But I just don't know why people get that whole mentality that people have, that a small minority have, that going on to a conversation with 50 odd people and you sort of trying to hijack it. I might have thought differently in a different age, but currently my very sensible nature says that's a terrible thing to do. How are we doing on time? Oh, one more minute. So the benefit of having the mics open, if you've got a question, you can just pile in and ask it. If you've got anything going on, such as the cat attacking you or someone eating their dinner or watching the TV next to you, then please go on mute if you've got background noise. But if you haven't got background noise, then leave your mics on. It saves having to teach you how to use raising your hand or the sound of people clicking on their keyboard as they're entering messages, or me responding by clicking on the keyboard. Cool. We've got 11 people, and 2 of them are me, so we've got 9 people. So that's good. Cool. 7:30. Shall I kick off then? Yes, I shall. Okay. Right. So we run this session with for Bath astronomers, for anyone coming along every 3 or so months ago. 3 or so months. We ran one in January, and we were due to run one in March, whilst it was still reasonably dark skies. But that all got cancelled. So we've switched to Zoom. So hopefully it turns out to be equally productive, and hopefully the video that we've got here stands up. Okay. So I just need to click on that and pass there. This is me. Now, everyone hopefully has got an astronomy shed. If you haven't, it's one of your first things to do. Get rid of your lawnmower and all that kind of thing, and fill it out with all your astronomy gear. Now, this is a bit OTT. There are sheds in my garden, and one of them has astronomy kit in it, mostly because my wife won't allow me to have so much astronomy kit inside the house. But you can get a little carried away, like a lot of hobbies, a lot of sports, whether it's cycling or football. There's kit involved in it. And so you just need to be a bit mindful when you're buying stuff that you've got somewhere to actually store it. I'm not the only person in Bath Astronomers. So here's the committee of Bath Astronomers. There's Dennis, Charles, what am I talking about? Dennis, Chris, we've got Jonathan, Abby, and then myself on the side. And we look after Bath Astronomers and help it to run as effectively as we possibly can. So if you see any of these people, whether it be in a lecture or whether it be a lecture or out on the street, please stop us and ask us about the night sky. Hopefully we can help out, and hopefully we can help your entry into astronomy. So as I said, if you've got any questions as we go along, we've got one, I'm getting a bit of feedback. I'm not sure who I'm getting it from. So if someone, I can mute you all, just to see if that gets rid of it. You can unmute yourselves, but hopefully that'll get rid of the feedback. Yeah, I can't hear it anymore. Well, you can unmute yourselves if you do want to ask a question. Take questions as we go along. Hopefully it'll last about an hour. If you want it to last longer, then great. If you want it to speed up, there's even a button in Zoom for asking me to speed up. But hopefully it'll be the right pace. So I just wanted to give you a little bit of a flavor of the night sky. So what I'll do here is just play you the night sky last night. This is over Odd Down in Bath, and this is an all sky camera, and because the moon is so bright, you can see it's actually lit up the surface of the camera that's taking these pictures. And it takes a 30-second picture, or I think maybe 25-second picture. Oh, so yeah, it's 25-second picture all the way through the night, and it adds them all together and creates this video that you can see. And normally you'd see lots of aeroplanes flying over this, but there are none. There's actually one or two during the night. But the biggest thing you see down the south, oh, there's a big thing whizzing across. That was probably the International Space Station going across. And that's a whole night. That's what a night looks like currently over the West Country. And to give you a bit more of a flavor, some of the photos that we've been doing over the last week or so, just to see what could you see if you became keen on astronomy. So this is the crater that's right in the middle of the moon. It's called Copernicus. And what you're looking at there is about 100 kilometers in diameter. And if you look into the middle, you can see the mountains that are created or were originally created from when the impactor, the asteroid, smashed into the moon, and the center of the crater acted like a liquid. And if you've ever seen a slow motion of a water droplet, you'll note when it hits the water, it makes a crater, but then a little bit comes out of the middle, a little droplet comes out of the middle again, and that's why you have mountains. And if you look at all the craters in that picture, typically you'll see little mountains in the middle of them, and it's that process that causes those. A few more photos. So this is a chain of craters that's on the moon. It's about, this will probably be 3 or 4 days into the lunar cycle. The top crater is actually named after the astronomer who lived in Bath. This is the Herschel crater. And Ptolemaeus, Alphonsus, and then Arzakiel are down here. These are all taken with kit from just taking photos from Bath up in Odd Down. So what else have we got here? We've got near the bottom of the moon, we got a crater called Clavius, and at certain times of the month, sunlight pours in over the edge on this side here and illuminates just the edges of these craters, these two big craters in the middle, and you get a big round hole of blackness and two eyes peering out of it. And so they're called the eyes of Clavius. And the other one that you might know is at full moon, you see lots of white streaks across the moon. They're from one crater typically, and that's Tycho. And this is the Tycho crater, which is seen not at full moon, but just before first quarter here. So you can't see the ray system going on. What else we got here? You can see up here we've got Plato crater, and there's a big valley carved into the surface of the moon. It's about 160 kilometers long, and it's called Valles Alpes, and it's a fracture, probably from when this big crater around here was formed, which is called Mare Imbrium. And with an ordinary home telescope, you can actually, with an eyepiece, make out that inside this scar in the moon, there's actually a little valley that runs up it, and that's a volcanic fissure that goes up. So you can actually start seeing some of the volcanic history of the moon as well. And here's an interesting thing. It's called the Straight Wall, and it's where the lava inside this huge mare has slumped and compressed. This is probably the most interesting thing on at the moment. This is Venus, very bright in the night sky. It has been for the last few months. And again, with a home telescope, you can see this. I'm not sure I should dare, but if you just bear with me, I'll see if we can get a live view of Venus now. So I'm just going to stop the share. And I'm going to see if I can get this going. If you just bear with me. So I have a link through to the telescope outside. And if I'm lucky, I might be able to patch you through so you can actually see what the telescope's seeing currently. There it is. It's actually running. Yes, it is running. It's slow, but how to do this? Do I have to pull this over to here? I think that's what I have to do. Yep. And if I hopefully, haven't got the screen. Oh, there it is. My desktop. Got part of the remote desktop. So if I can see if I can pull that back in. Does that bring it into this screen? Yes, it does. Okay, that's actually live. That's Venus now that you're seeing. So that's through a telescope in the garden. It's got a camera on the back, and there's a computer attached to that camera, and I've just linked this computer through to that computer so you can see that. So there you've got Venus. It's heading between the Earth and the Sun at the moment, and called an inferior conjunction. And at that point, it's like a reverse moon. It's getting, the crescent is getting thinner and thinner and thinner and thinner. So we've actually got about 2 weeks left of it, and then it'll actually be like a new moon. Venus will be gone for us. We won't be able to see Venus anymore. Okay, let's stop that and go back to presentation. Hopefully we're back to, there we go. There's other things. So a few weeks ago, just popping out into Bath, you can see even despite the moon, the cloud and the bright moon that we've got here, there was Mars on view. And the reason why I went out to look at this one is there's a star that's very red in color, just like Mars, and it was going to be quite nice to see them together. The other thing you can see about this is the light pollution that you've got in Bath. So there's quite a lot of even thin cloud that's lit up a bit like a Christmas tree because of all the street lighting that's on at night. Here's slightly less cloud in this one, and in this photo we've got Mars, we've got Saturn, and we've got Jupiter. And if you look really carefully at Jupiter, you might be able to see the dots, and they're the moons. So those, you can see the moons around Jupiter. And that's just with an ordinary camera. I think that's a 300mm lens on there. So nothing particularly special about that one. So there's lots to see. And here's another thing. So I said we might have seen the ISS last night. It was due to be going across. And here it is actually going across back in March time. So you see a big bright streak. It takes several minutes to come past. And these are reasonably long exposure, say 25 seconds that have got that. And hopefully you've all managed to see the International Space Station recently. Okay, so that's just to give you a bit of a flavor of what's been going on over the last month or so in terms of stuff to see. There's been other stuff. There's been a comet called C2019 Y4 Atlas. And astronomers at the beginning of March thought it was going to be one that you could see with the naked eye. Come the end of this month or so, it's turned out that actually it faded suddenly, and they were good enough to turn the Hubble telescope round on it, and it's disintegrated. The comet is no more. So you always get stories about really bright comets, and occasionally they do pay off, but for the last 15 years or so, we haven't actually had a bright comet. It's about time we had one. So let's kick off with a little bit of education, or hopefully just an overview of what you can see, but without going into all the kit and all of that. Sort of how can you actually enjoy the night sky? And what can you tell? So let's start off with the minimum of equipment that you might actually have or want to use. And for me, the minimum kit is going to be a park bench. So what can you do with a park bench? Well, you can sit down, you can look, you can sort of enjoy the view, but with little more than that and a ruler. Back in around about 300 BC, a chap called Aristarchus looked out and actually managed to work out that the Earth wasn't the center of his world, his universe. It was the sun. So Aristarchus of Samos, 300 BC, did that, and his work then kind of disappeared for a long while, whilst people suddenly thought that Earth was actually still the center. So it took a long while, but essentially he did that just by observation. But what can we do from our little park bench? Let's see if we can do a little bit of science. So the first thing we can do is try and solve that perennial problem. Is the Earth flat, or is the Earth spherical? Which is it? Now, there's a lot of people in around the world that are still debating this particular one, but for my little park bench, my seaside bench, I can actually solve this particular problem. So how am I going to go about solving it? So I'm going to need a park bench, but I'm also going to need some friends. I'm going to need 3 of these people, 3 groups of park benches, and I'm going to need to separate them by quite a distance, a few hundred kilometers. But that's well within possibilities. If you know someone who lives in Paris and you know someone who lives in Kent, say, you could perform this experiment and sort of work out if the Earth is flat or if the Earth is round. So if it was a flat Earth and the sun was very far away, if the back of the bench, which I've marked in red here, we got the sunlight coming down in yellow. If the sun was very far away and we lived on a flat Earth, we'd have an angle that the shadow made. Let's call it alpha. And another shadow on the second park bench, a few hundred kilometers away, that would also be alpha. And the one in Paris, that would also be alpha. So we could tell if we lived on a flat Earth and the sun was very far away, if all the angles are the same. But we do that experiment, we phone each other up and our angles are different. Okay, so the flat earthers, it's because the sun isn't very far away. The sun's really close. It's a big light that NASA put up there. Okay, so we now know that the sun is really close. So let's measure those angles again. We got for the first bench alpha, we've got a beta, and we've got a gamma. Right, so that's great. We could do that. Our friends have told us what angles they measured, and we can get a piece of paper because we know how far apart each of the benches are, and we can draw those lines out proper. So we draw our first line, go to London for our park bench, and we draw our line in. Oh, that must mean the sun's here. Where the two lines cross, that must mean that's where the sun is. Oh, we do our third bench and it doesn't cross where the other two cross. This means that you can't have a flat Earth. So we've got neither a flat Earth with the sun far away or a flat Earth with the sun close to us. So our park bench has solved our first problems, which is cool. So the Earth is definitely round. We could have had a shortcut back in 2012 and talked to a chap called Philip Baumgartner, who took a hot air, or actually took a helium balloon up to 39 kilometers high and jumped out of it. He had a lovely view of the round Earth, but this particular problem was solved a lot earlier, actually in 240 BC. So let's see how the problem was not only solved but taken a bit further. So here we've got Aswan, which is in Egypt, and it was noted around 240 BC that at a certain time of year, the sun fell vertically down. So you actually lit up the bottom of water wells within the region. So that's interesting because the maths we've got at the moment is very Pythagorean. So trigonometry is all about right angles. And so if we've got our sun directly above us, then we can start thinking about making a right angle because our horizon and that sun make a right angle. So what he did, this is a chap called Eratosthenes. He was aware that on a certain day of the year, the sun was vertical in Aswan. So he went to Alexandria and he measured the angle of the sun and the shadow at Alexandria. And he knew the distance between Alexandria and Aswan. And from that, clever chap worked out the distance between, or the distance that would go all the way around. He worked out that the angle that you see in Alexandria is the slice of the pie of Earth. And he knew the distance between the 2 points because it had been measured in stadia, ancient units. We're not absolutely sure what a stadia is. There's a couple of interpretations. One of the interpretations means that he'd be 16% wrong. So he got the figure within 16%. That's not bad for 240 BC. The other interpretation suggests he got the figure 1% wrong. So either way, just by measuring the angles that the sun makes, the shadows of the sun make, you can actually work out that not only you're on a round thing, but you can also work out its diameter of around about 12,700 kilometers. So we're not too bad from our park bench with just maybe a little protractor that we had at school and maybe some very simple maths. We've worked out not only is the Earth is round, but we've worked out its diameter as well. So what else could we potentially work out from our park bench and looking out at the sun? Well, the first thing we might notice is that if we have our lunch there every day in the winter, we watch the sun rise over in the east, and that the sort of pinkish line is the track of the sun through the day. And at midday, it's due south, and we watch the track go off. And if we made a mark with a stick of the height of the sun, and then we came back 6 months later, you'd notice the sun took a different path through the sky, from east to west again, but this time a lot higher in the sky. So what can we observe from that, from the difference between these two solstices? Well, we can measure with our protractor again, and we know it's 47 degrees between those two. There's got to be something that's causing that. So let's have a think. We know we're on a round thing, and we know the sun is big and we go round it. So if we tilt the Earth, that would explain it. If we tilt the Earth by 23.5 degrees, then that would explain why we see the sun at different places. So if we take the winter, which is over on the right-hand side here, and for someone in the UK, we're about here. And if I was looking at the sun, let's assume it's in the middle here, then it would appear low in the sky. If I take the UK again over here, go to the sun, it would appear higher in the sky. And that difference is twice the angle that the Earth is tilted over. So we know 47 divided by 2 is 23.5. So we've worked out a lot. And the other thing we can tell, well, that explains why winter nights are really long, because we've got a nice long white line here, and summer nights are really short. So lots has been explained. And again, all we've got is a protractor, park bench, and a lot of sandwiches to take us through the entire year. This starts getting even more interesting for astronomers, because here we've got a diagram. Up the side is the hours of the day. And then we've got how much nighttime you get, how much daytime you get. And we've got the change from wintertime into British summertime. And you can sort of track how much nighttime is there. And this is to do with the way that the Earth goes round. So at the winter solstice that we have over here, then we have maximum nighttime, because the sun is the lowest in the sky. So when it goes round, when it's our night, it's very low below our northern horizon. So we get nice, long, dark nights. And during the summer solstice, it's the other way around. So it's very high. And so during lunchtime, so when it comes around to midnight, it's actually very low, but below the horizon in the north. So we actually lose proper nighttime, and we lose proper nighttime in about 2 weeks. So in about 2 weeks' time, there will be no nighttime. It's officially, there's no nighttime. Nighttime is on holiday. We're in twilight, which is where the sun hasn't gone that far down below the horizon. For 2 months, each year, we actually have a twilight, and it's called astronomical twilight. And it's the main impact is it's harder to see very faint things in the sky when it isn't particularly dark. So it's quite hard seeing things like galaxies and nebula at this time of year, but other bright things are perfectly visible. So we just keep an eye on that. And some people ask me why I always vary the time on astro meetings. Why do I start them at 4 o'clock one month and then 6 o'clock another month? I actually start them to follow when astronomical twilight is beginning. Actually, I do it astronomical twilight is just beginning on this interface between these two grey lines. And so the timing of when we actually go out observing is there. We always typically start around there. It means it's still light enough to set up all your kit, to get your stuff out of your car, but it will quickly be nighttime. So that's why we changed the time going through. Because if I had the same time all the way through, let's say 8 o'clock, then there would be a lot of nighttime in the winter where we could have been observing. So then we have it a lot earlier. And things like outreach for schools, it's great because it can still be school time or just a little bit after school time, and we can be stargazing, which is really kind of fun. So the different types of twilight are all organized by how far the sun goes down and below the horizon. So in the winter, it goes down very far, but in the summer, it doesn't. It doesn't actually get below about 16 degrees below the horizon in the north. And so in summer, you always see it's slightly light in the, even at the middle of the night up in the north. That's because the sun hasn't gone that far down. So if we have a look at the night sky, and if you look through an entire day, oh sorry, an entire evening, you'll see this kind of typical thing. If you were to take a photo every 15 minutes and then glue all those photos together to make a little movie like I did with that all sky shot above Bath, then you'd see it all go around. The interesting thing is something's happening. Lots of stars are moving, but one isn't, and it's that one. It's actually moving a little bit, but not that much. Oops, sorry, that one. I've got to point to the right one. It's that one. It's not moving that much. And that's the pole star. That's Polaris. So why does Polaris not move? Why does everything appear to spin around Polaris? There's got to be a reason for that. So let's have a think about, we know on a big ball, we know it's inclined. So let's draw the axis of rotation and the equator we've got here. Okay, so, okay, I'm up here somewhere. So let's draw a line to me. So this is where I'm sitting up near the UK. And if I draw my horizon in there as well. So when I'm looking up at Polaris, I'm actually looking at that line there. Polaris is on a line that's parallel to the Earth's rotation, axis of rotation. And because of that, everything appears to rotate around it. And if you look at that, if you were any good at maths at school in terms of basic trigonometry, that and that are the same angle, which is quite interesting because it means that's your latitude. That's how far up on the Earth you are, how far from the equator you are. So in the northern hemisphere, you can always find Polaris because it'll always be at the height which matches your latitude. So for us around here, it's around about 51.3 degrees. As you go further south, then that will change. You go down towards 0. As you go up to the geographic North Pole, then and your latitude approaches 90, then Polaris will be directly overhead. At the equator, Polaris will be on the northern horizon for you. So let's say you're kidnapped and you wake up in the middle of the night, you break out of, and you've been taken somewhere in the world. Well, at least you can find out your latitude very quickly if it's not a cloudy night. The other thing you can do for your park bench is just look out at the same times. Let's say we looked at 9 o'clock every night, exactly 9 o'clock, and we took a photo. But we'll notice it's changing. And that's because the Earth is going around the sun. And so when it's facing away from the sun, because it's midnight, let's say, then you're actually looking at a different part of the universe, a different part of our galaxy. And so we've got the galactic plane showing there. But we have a day that takes 24 hours, and that's a day is 24 hours for us to go around the sun. If this is moving around, it means that the actual day measured from, let's say, a particular star that we have, say Betelgeuse in Orion, it doesn't take 24 hours for Orion to get back, or Betelgeuse to get to the same place again, and it takes 23 hours and 56 minutes. So actually, when everyone tells you a day is 24 hours long, only with respect to the sun, to the rest of the universe, our day is 23 hours and 56 minutes. And that's why we see a different view slightly every night. It just moved around a little bit. So what else regularly moves? What else can we see from our park bench as time goes by? We actually see that some of the stars are moving as well. They're not stars, they're planets. There's other things that move. There's comets, there's asteroids, but the things you can see with the naked eye are typically the planets, the wanderers. So each day, each month, they're in slightly different positions. So at the moment, Mars, Jupiter, and Saturn are in the morning sky, but over the months, they're actually going to come into the evening sky, and you're going to be able to see them with binoculars and telescopes in the evening sky as well. They also do weird things. They don't all seem to move in one direction. Sometimes they seem to go backwards. Sometimes seem to do loop-the-loops. And as we saw with Venus, the ones that are inside us actually have crescents. So they act just like our moon. So Mercury also shows phases. So Mercury and Venus are the two planets that show us phases as well. And we can see those with telescopes. And Venus currently you can see with binoculars, and you can see with quite good telephoto lenses on cameras as well. So there's lots of stuff that's changing night to night all the way through the year. And again, if we have a look here, what else will we see in the night sky? Well, we'll see shimmering stars. It's that twinkling that people talk about with stars. That's to do with the Earth's atmosphere. It's called scintillation. And it's the way the Earth is traveling through thick layers of atmosphere, which causes the light to bend and refract, which gives you a shimmering effect and slight changes of colors. And we see there's some bright stars, and we can see there's smaller, dimmer stars as well. So the stars change in brightness. And I've got the Milky Way. I'm very much enhanced it here. You'd have to be in the middle of Africa, away from any pollution, or South America, to see anything anywhere near that in terms of absolute brightness. In fact, I've amped up a bit more, so you probably wouldn't see it ever quite that bright. But you can see it quite well. You can see the Milky Way from Bath without too much trouble. So we've got to look at a way of recording how bright stars are. And so we have a magnitude scale that actually dates back to ancient times. And it's just a times 100th scale. So one star compared to another star. So magnitude 1 compared to magnitude 6, it's 100 times brighter. And so everything, whenever anyone talks about brightness in terms of the sky, they usually use magnitudes as this scale. And it's an ancient scale. And just to give you an example, typically stars are magnitude 1 or higher. And the best you can see with the human eye is about magnitude 6. The sun, by the same scale, is magnitude minus 26, and the moon 12.5. At the moment, Venus, if you want an example, is minus 4.2, I think. So it is the second brightest thing in the sky, in the nighttime sky, other than the moon. So it's, I suppose, does everyone looked up in the sky and thought, well, what is that? I don't know what that is. So we've got to have a way of finding stuff in our nighttime sky. And one way that is used by scientists and is, for the last, since science came to astronomy, for the last 300 or 400 years, they've come up with a way of, let's have some coordinates, like an X, Y, of where something is in the sky. And one of those coordinate systems sits with Polaris at the top of it. And it's called right ascension, which is how far around you are. And we have declination, which goes down. And that means for every star, then it has a pretty fixed right ascension, X coordinate, and declination, Y coordinate, and XY. But they're really hard to remember. And so there has to be a simpler way of doing it other than remembering all of the things. So they came up with a solution a very long time ago, and that's these. The constellations of the sky. they've been varying for thousands of years. And there's been attempts to date the earliest constellations. Um, the ones that are based on antiquity, because they seem to go a certain distance down the sky and they haven't got anything in the southern hemisphere, by how far down in the sky they've actually made a constellation, you can kind of work out what latitude they were at. And this is all around Mesopotamia and Babylonia, the original ancient constellations that we still have a few of or artifacts of date back to there, because again, from the latitude, we can work out how far they could have seen down and where those constellations were. So that gives us a good guide. Now, there's been over 100 different constellations suggested over the last few hundred years. People named them after benefactors, after kings, for all kinds of reasons. But in 1927, it was in the 1920s, the International Astronomical Union formed. And to get rid of this problem of things had two names, then they came up with a list of 88 constellations to cover both the northern hemisphere that we get to see and the southern hemisphere as well. So there are only 88 to learn, but they can be a bit fun to learn. Some of them look a little bit like they're supposed to be. So we've got Hercules here. That's supposed to be a person. That isn't too bad. And this is Cygnus, the swan. And so if you imagine those are the wings, and this is the body and the head of the swan, then that isn't too bad. The bear, which is the plough. So the tail and the back leg of the bear. This is actually the rump of the bear. The bear actually extends further up here, and his front foot is down here. So we have constellations, 88, but we also have things called asterisms. They're more helpful ways, things that are a bit easier to remember. So the one that hopefully, or a lot of people will know, is this one. It's actually part of Ursa Major. It's the plough. And it's the friendly saucepan that people know. That's an asterism. An asterism, you could make up your own asterism today, go out tonight, have a look and say, that's a shape of a kite. I'm going to call it the kite. And that's your asterism. And so asterisms are being made up all the time. There are lots of survived over hundreds of years, but several are actually only decades old from when amateur astronomy became a very popular thing from the 1950s and 60s onwards. Some of the asterisms that people know are based on that particular time. So we can learn our way around just by seeing shapes made out of the stars, which is very, very useful. And that's the way I do it. I don't use coordinates. Only when I'm setting up a particular type of telescope will I actually use coordinates, or when something's moving a lot. So comets move a lot from night to night. So I might actually use that XY coordinate to find a comet rather than using the constellations. Just because it's a bit more accurate and it can get me to see things. But the other thing you can do, constellations are great, but you want to know how big is something that I'm looking at, or how far away of it is it from that particular bright star that you know of. And there's a handy trick that you can do. And luckily you were fitted with the handy trick from birth, and that's this. So if you hold up your finger like that, and you hold it up at arm's length and hold that towards the sky, that'll actually cover 2 widths of the moon. So people with a smaller frame tend to have smaller fingers and shorter arms, and so it tends to work out for everyone. If you have very long arms, you tend to have bigger hands. So that's the way it generally works. But it's really useful for saying there's an interesting galaxy and it's about 10 degrees away from a very bright star that you might know. And so what I do there is I just hold up my fist to there, and that would be my 10 degrees. I can do 15 degrees, well, actually 20 degrees, sorry. which is stretched from there to there, or straight up is 15 degrees. So there's lots of different ways of doing that. And one of the easiest ways is if a planet is rising and someone says, go out and look at 6 o'clock, they might tell you it's 20 degrees above the horizon. So you don't need any gadgets other than your hand to walk outside, look in the right direction, hold your hand up to the horizon with your thumb on the horizon, then the object is going to be somewhere around your little finger, okay, when you look around. That's a really easy way of finding stuff without having too many gadgets or anything like that. And the other thing you can use your finger to do is, if you've ever looked at the moon and it's looked particularly big, it's supposed to be it's coming up to a supermoon, as a full moon at the moment, and it looks bigger next to the horizon. Again, hold your finger over it. You can use your little finger or your little finger sideways on to cover it, and then wait a few hours until it's risen up and cover up with your finger. Although it looked to your eyes that it was bigger by the horizon, it is still the same size. So it's just an optical illusion that it looks a lot bigger. And if you do this with a supermoon, and you do this next month when we don't have a supermoon, you won't be able to spot the difference. Supermoons are very hard to see that they're any different. You feel that they're different, but the actual increase in size compared to how tiny the moon actually appears in the sky is so little that it's very hard, even for a hardened observer, to actually spot the difference and discern it. So it's about 20% at the best case between the smallest moon and the largest moon, about 20%, but it's not always that different as well. Okay. So the next section is all about tooling up. I noticed some questions. I haven't got my chat screen up, so let's just see on that. If you have any questions, then please feel free to unmute yourself. Aha. So let's go through some of these questions. So, Belinda, you asked ages ago, can you ask a question? Of course you can.
Okay, so we've been having a little conversation on chat, so my question's been answered.
Oh, okay. Oh, Chris Brooks has been.
Yeah.
Thank you, Chris. Do you want to take over? You're doing a great job. Okay, so the next thing I want to move on is actually, so everything you could have done so far, you can actually do just by pure observation. You don't need anything more than your eyes to actually start enjoying things. So meteor showers are open to you, observing the differences in the moon, bright comets. There are certain types of weather patterns which are very high up in the atmosphere. The one that's currently just starting is called noctilucent clouds. It's ice crystals about 70 kilometers above the Earth, and they glow an electric blue. You don't need anything to observe those. Just go out between an hour and a half to 2 hours after sunset or before sunrise and look to the northwest at sunset and the northeast at sunrise. And if you see electric blue clouds quite low down, remember what I taught you about 20 degrees? Let's do that again. 20 degrees, about that. About 20 degrees is the maximum they get. So you need quite a good northern horizon to do it. But if you see electric blue clouds and the sun isn't up, you're watching noctilucent clouds, which are much, much higher than normal weather, 70 kilometers high. So you can see all of those. There's other things, the International Space Station, you can see. And unfortunately now you can see the Starlink constellation of satellites that are regularly coming across our skies as well, in big streams of 60 satellites at a time. And so you get to count them one. And then depending on when they launched, maybe 10 seconds later, the next one will come past, and you just keep counting. And if you can count as far as 60, then you see it. But that's just with this particular machine. That's with our eye. This is better than any camera that I've got to use. there are 90 million, or actually about 100 million sort of sensors within each eye that you've got, which is a lot better than your 24 megapixel. It's at 4 times better in terms of resolution than your camera has got. Of those 100 odd million sensors, 90 million of those actually pick up just black and white. They only pick up whether there's a light has hit it. They don't pick up whether it's color. You've got between 7 and 10 million color sensors in your eye. So your eye's really quite good at picking up things in terms of grayness, shades of things. It's not actually that good at picking up color. And one of the consequences of having 90 million rods in your eye and 7 million cones in your eye is in astronomy, where everything's a bit dark and faint and there's not much light getting through to your eye, you get to see shades of light and dark. You don't typically get to see many colors. It's just purely because your eye is equipped, it's only a certain size, your eye, and it's equipped with so many sensors that pick up black and white, or shades of black and white and gray, rather than the cones which pick up the colors. The cones, they fire a lot quicker, and the rods are a bit slower. You can't have as such a dense sort of network in terms of sending each pixel. So the rods are sort of connected together. So you actually need a few rays of light to hit rods before they'll fire off as a group, whereas the cones will typically actually take 10 or so photons or so to fire off. So they also have slightly different sort of speed ratings as well. And the other thing is that when light comes inside your eye, the first thing that happens is you've got a lens at the front. And what lenses do is they flip everything upside down and left to right. So everything we see is actually projected upside down into the back of our eyes. But they're not bad, because if you think the furthest we can see is something called the Andromeda Galaxy, which is a bright smudge in the skies that we can see from the UK. That's 2.5 million light years away. So your eyes can see 2.5 million light years. So that's not particularly bad. Have they got any problems? Well, not too many. I say the rods pick up black and white. The cones you've got 3 varieties of. You've got a kind of a blue one, kind of a green one, and kind of a red one. And they have different sensitivities. So it's quite important to understand about the sensitivities. So here's a graph, and I promise it's the only graph I've got. We have the sort of the up-down scale is how sensitive our eye is, and then across the bottom is the color or the frequency of light that's come into our eyes. So the blue line is those cones that are sensitive to blue. The green line is those cones that are sensitive to green. The red line is those cones that are sensitive to red. But you can see there's a lot of overlap. And so these sensors are picking up. So we interpret color in a very human way. Aliens will see color potentially in a different way. It's just because of the way things overlap. And our rods, although they only see degrees of light, black versus shades of gray all the way through to white, they're actually quite sensitive to around about the green area of the spectrum. So we're quite good at seeing very dim green, because that's what our rods in our eyes are good at. So why do I show this? Well, has anyone ever wondered why astronomers and people on submarines or on bridges of ships and things always use red lights? It's because of this. If you have a red light, it only actually affects the red end of your vision, which is a part of your green cones and your red cones as well. Those are the two that are affected, but it's right down on their lowest sensitivity. So it hardly affects them at all. So you can operate machinery, you can operate, you can read books, and you're not interrupting all of this sensitivity here. Now, the reason why that's important is every time a photon hits your eye, there's a chemical reaction that occurs, and that chemical reaction sends the trigger through to your brain to say that you've actually seen something. It takes a while for that chemical to be recycled, anywhere between 5 and 20 minutes for that chemical to be recycled. So if you get to see a lot of blue light or any of these other lights high intensity, it uses up all those chemicals, and you're just left with a very depleted store. So you actually lose your vision, your ability to see. So what happens is the eye effectively goes on a go slow until it gets all of those chemical stores back again. So if you see a lot of light, all of a sudden, or over a period of time, then all of those chemicals will be very low within your eyes, and your eyes will not be sensitive at all. And the one thing you need in astronomy is sensitive eyes, because we're looking at dim things. We're looking at dim features, stripes on planets, dark patches in the Milky Way, features within a galaxy. All of these things can be very dim. So if we've used up those chemicals, there's no point us actually even trying. We might as well wait until they've fully recycled, which is typically you'll start seeing the benefit after about 5 minutes after that. So the instance it could possibly happen, or most likely happen, is if you're out and then suddenly someone switches their headlamps on in the car. And what that's doing is white light is made up of blue, green, and red, all the frequencies across depending on what the light source is made of, and that has just used up a great deal of the chemicals within your eye to be able to see. So you go down to a bit of a go slow in terms of your ability to see. You cannot see fine detail now, and it'll be between 5 and 20 minutes before you can see any fine detail. If you're operating with red lights though, this effect doesn't happen. So if I go back, so if everything is illuminated by red lights, yes, I'm consuming chemicals, but at a very slow rate. And that isn't ongoing. So I can actually keep good vision all the time while still completely surrounded in red light. So that's why we use red lights. That's why we use red torches. That's why hopefully all the LEDs on things like telescopes are red, to stop this happening. And so it's quite important to make sure that you look after your eyes. So with the advent of smartphones and things, this is quite difficult to actually use those. So a lot of the astronomical apps have red modes, and also some of the phones now, iPhone, give you the ability to change the backdrop and the color, so it's all red tinted. They will still be operating in a longer, so if I've got a special red torch, red light torch, it'll be operating very much in this area. But if I have a display from my iPhone, it'll actually be coming out over here. It'll be a wider band. Although it'll be mostly red, it'll still be coming and using a lot more. So really, we have to, if we are going to use smartphones, yes, use them on red screen, but very much minimize their usage, because it is not as good as a proper red light, which isn't taking away your night vision. And it becomes a bit difficult because doing photography and things and setting those up in pure red light can actually be a bit of a pain, but it's worth it just to keep your night vision. Okay. So I'll move on to other kit. So the first kit really I'd like everyone to consider buying or getting is a good set of binoculars, or a reasonable set of binoculars. I say a reasonable set because I drop them all the time. And you don't want to buy secondhand binoculars from me. So I buy ones that are good enough to do what I want to do with binoculars. In this case, it's fine stuff. I'm not going to spend too much time because typically I'll go back to a telescope. So I'll have a pair of 10 by 50s. I used to buy them from Blacks and Millets. They used to have a very good cheap pair, but they don't anymore. So I actually buy secondhand binoculars off the likes of eBay, and you need to be a little bit careful. Again, if they've been knocked, some of the prisms can be out of line, but that's a reasonably good source. If it's going to be your primary tool, then you want to pay a bit more money and get a proper pair of astronomical binoculars. It's worth it if that's what you're going to do. If your intention is not to buy a telescope for a good while, if at all, then good binoculars. And again, 10 by 50s is a good pair. You can get something slightly smaller. The first number, 10, is the amount of magnification, so how much bigger things appear, and 50 is how wide the front of the binoculars are, that lens. So 50 millimeters is that. So that's the 50 in the 10 by 50 and the magnification. There's lots of design points in them. The cheaper ones don't have any of the good design points. So in this case, the focus is actually central and it pushes out the two ends of the binoculars. Very typical way of designing binoculars, but it's not so great if you are doing some really detailed trying to focus in and make sure both of your eyes are perfectly aligned, because every time you focus in and out actually moves slightly differently on each of these sides. But we've got a talk by Steve Katonkin coming up next year where he'll be able to guide us a bit more, and he does some really good talks on binocular astronomy. But what is a binocular? Well, essentially it is a telescope, one, and two. It's two telescopes bolted together. And the big benefit is, the big benefit is the amount of light that's gathered is significantly more than my eye normally gathers. So it's like a big bucket. It's gathering up more light and it's pushing more light into my eye. So I can see more, I can see dimmer things. So the magnitude limit I've got on just with my normal eyes is about magnitude 6. But with binoculars, you can get down to potentially magnitude 8. And with very good binoculars, you can get further than that. So much, much dimmer. It's like so it's about 5 times dimmer than you would normally see, 5 or 6 times dimmer than you normally see with your naked eye. So that's really good work. But also, of course, I typically go for, let's say, the eBay ones, but you can get them from lots of different places. In terms of telescopes, your choices, well, Newton came up with a great design in the middle of the 17th century, and it pretty much hasn't changed much. This is Newton's design, a Newtonian telescope, and it's sitting on one of these push-me-pull-you mounts. It's a Dobsonian, which just goes up, down, left and right, and you just yank it around. It is bulletproof, absolutely amazing things. But the problem is the Earth rotates, so you're constantly moving your Dobsonian around to keep things in. So you have to move it both in up and down and left and right. So they then invented the equatorial mount. Now this rotates with the Earth. So this will rotate with the Earth, but typically the equatorial mount is manual. And so you actually have to twist. But instead of doing up, down, left and right, you're only just twisting and moving things to the right ever so slightly. So it's a lot easier to control once you set up, and a lot easier once you found an object to keep it within the field of view with an equatorial mount. But it's more faff setting it up. It's you have to make sure it's pointing towards Polaris, so polar aligned, to get the most benefit out of it. But I've got lots of these different mounts, and they're very, very useful. If you want to go the whole hog, then you can get something to hold your telescope, which is a go-to mount. So it's an electronic system that it'll go through certain rules in terms of where are you? Please point me at the North Star. What time is it? And you press go, and then it'll ask you to find some stars and it'll work out where you are. Or the clever ones, like Chris has got, it just says find 3 stars. And it's got a map of the heavens in it, and it can work out, because there's only the chances of 3 stars being in exactly the same positions, the difference between them actually allows you to work out exactly where you are just from the difference between 3 bright stars. So you don't even need to know what the star's called on the modern go-to telescopes, whereas some of these older ones like this picture, you actually have to know what the stars are called to find them. So these go-tos are great, but they cost money. The cheapest is the Dobsonian, then the equatorial mount, and then the equatorial go-to is the most expensive. So really, what should you be buying now? Well, for me, really, it's nothing. A pair of 10 by 50 binoculars is a great way to start, and start looking through other people's telescopes rather than immediately going out and buying something. If you really want to, then get some advice and go for it. But get something which has got a resale value. If you buy something from Argos or something very cheap, probably hasn't got any resale value. You won't be able to recoup any of your money. But if you bought something more sort of lower to mid-range, then you potentially have someone that wants to buy it after you've used it, and you want to perhaps buy a different telescope. This one isn't up for sale yet, but you never know. It might be up for sale in the coming years, but I'm not sure we can afford, especially as a society, to keep it running. But to give you an example of some of the costs, here is the price list from last year, or from various telescopes. And you can see that the ones that are on this Dobsonian mount, so this type of telescope is the Newtonian type of mount here, is quite cheap, mid-range, sorry. But as soon as you start going to fancy amounts, then the price racks up. The actual, in this case, the telescope that's actually on them is exactly the same. So the difference between a 6-inch telescope at £200 and this 6-inch telescope is at 550. You're paying over double, nearly 3 times the amount, because of this very expensive go-to mount. We'll show things for you. So if money isn't an object, then as far as the first telescope, I'd be recommending either of these first two. And then depending, if you wanted to learn the sky, I'd recommend going for the lower area. It's not to say some of the smaller telescopes don't have value, but if you're really keen, you'll probably grow out of it. So it's one of those ones whether you buy slightly higher up to start off with and you essentially grow into it, or you buy something that you can sell on and then move on to something like this. There's lots of people out there that will sell you telescopes. So First Light Optics, based down in Exeter, a very nice bunch. But there are other sales people, Harrison Telescopes, for the Valley Optics. So whichever interests you the most in terms of the deals they're doing. I'm not sure actually how many are open at the moment, how many are shifting boxes, whether they describe themselves as essential. I don't know. The one thing to be wary of, and this happens quite a lot, is just buying too much kit. So just be a bit wary of that. Try and start off small, or just as a single telescope before you start bolting cameras in. Have a few months getting used to it before you start getting too many gadgets, because it's quite easy to get lost and sort of lose hope. And so buy something simple, get used to using it, ask lots of questions, and then perhaps either upgrade the existing. So in this case, even in this cartoon, buy the bigger, let's say buy this as a smaller telescope on this mount, you could do. So, and then you could actually buy the bigger telescope and then use the smaller telescope you had as one to actually help find things as a sight scope. So you can actually plan how you might upgrade things as time goes on. Just want to show you a few practicalities as we come towards wrapping up. So it's not all sweetness and light, just pointing a telescope at the sky. So those photos I showed you of the moon to start off with, they were nice and clear, but on some nights, actually most nights, you'll see something like the left here, where the moon appears to wobble. And this is our atmosphere. Our atmosphere changes on a day-to-day basis and depends how bad it is. This actually isn't that bad. It's actually quite a good shot of the moon just gently wobbling away. And to get those really sharp pictures, what we do is we take a video, and that's made up of lots of frames. So we pick out the best frames of that video and put them together. That's where we get our really sharp images from. But they started off there's images like this of the different craters and things. And when you start magnifying stars through our atmosphere, you start getting all kinds of effects going on. And so if you just bump up the magnification on a telescope at one particular star, if the Earth's atmosphere is turbulent, that's the kind of thing you see on the right-hand side. So it depends on which days, how the atmosphere is, and if you try and push it too hard, you start seeing fuzzy blobs. The weather isn't always guaranteed. So actually some people who have the simplest type of telescopes, like this Dobsonian in the cartoon here, they can set up really quickly, and so they can be observing before the cloud comes in. Whereas if you have something more complicated like over here, you spend ages setting up, and when you actually start ready to observe, then cloud has typically come across. It's kind of horses for courses. I have two types of telescope purely for this kind of reason. I have the Quicken, I can set up really quickly, and then I have one that takes a little longer to set up. So I get this one, and I can be observing straight away if the conditions look a bit iffy. So this is the one I generally take everywhere, the Dobsonian telescope with a Newtonian on top. But to be guilty, I do have the other type as well. And the other thing that can affect what's seeing is, we mentioned it earlier, these are the Starlink satellites. I think this is group 3 of the Starlink satellites. And they're going through the constellation of Taurus, and this is the Hyades, the V of the Hyades, and this is the Pleiades star cluster up here, open star cluster. So what would have been perhaps a nice photo is being photobombed by the Starlink satellites. Now, can't be too cruel to the Starlink satellites, because in the same photo, I actually managed to capture 3 other satellites. So I caught 3 Starlink and then 3 completely separate. That's just a bit of a fluke that I managed to capture so many satellites in one shot. But that's becoming more common, and these Starlink satellites will become more common as well, in terms of getting in the way. Visually, it's quite nice to imagine the engineering and things that's going on and whizzing and what humankind's done, but it can be quite annoying if you're trying to create a pretty shot. There's lots of things you can look at. I say the moon is constantly changing through the months. So you see all these different craters that are highlighted, so you can look at those and look at some of the shapes the shadows create. So all the way through the month, the moon makes a really good target, and it varies in the distance from the Earth. So sometimes it's 28 Earth diameters away, sometimes it's 32. So we're actually coming up to the 28 point now. So it's quite close to the Earth. That's what makes it a supermoon, although astronomers don't like the word or the phrase supermoon. And just to give you an idea, so we might actually have a telescope where the moon appears this big within it. Well, what do all the other things look like if I had the same magnification on my telescope? Here's an example. Well, here's the sun, which is about the same shape and size of the moon. And I've inlaid what you can expect to see from the sizes of the other planets at their best. And so we've got Mercury here, we've got Venus, Mars, Jupiter, and Saturn going out. Uranus would actually, Neptune's probably about the same size as Mercury, and Uranus is slightly bigger, but I haven't got them on this picture. But you can get some reasonable images with sort of mid-range telescopes. And these are photos which have been enhanced. So again, if you screw your eyes up slightly when you're looking at them, that's what you'll see through a telescope. But over the coming months, we'll see these 3 coming to the fore. And so you'll actually see a lot more of them, Mars, Jupiter, and Saturn, over the coming months, all the way through into winter. And so with regular stuff going on and observing. Right. Who fancies going observing then? Have I wetted your whistle with enough information? Well, you might need a bit more information of what to do, what to go and see. So hopefully there's a lot of resources out there. You can just come and talk to any of those people we talked to at the front. So whether it's Dennis, Chris, Abby, Jonathan, or myself, anyone, there's lots of online groups to help. You can ask questions. We've got Facebook groups you can go onto. We've got some information on our website of what's going on. We've got weather on there, sort of phases of the moon, various bits and bobs which you might find interesting. So hopefully just a click away, such as this will show what the weather is like. So that dark, the black means that's really good. There's not going to be much cloud, and there's a small chance of rain that I can see from that. So that'd be quite good for the day after tomorrow's, if it were back in October. And there's other places doing it. So always check multiple places. So we've got clear outside here in the weather forecast. So weather becomes one of the drivers for what you can see. Although I actually just enjoy astronomy. So if I'm driving back from work and it's particularly beautiful sunset, I'll stop and look at it, or at night to see what's going on when coming out of the pub or whatever. So there's lots of things to do. We've got planisphere on the website as well, which tells you what the current sky looks like as well. But all of these are actually available in other forms. We've got a more detailed one on the website. If you go to the What's Up page, then there's various stuff on the phases of the moon currently, what the planets are doing, what time they rise and set, where you'll see them in the sky in terms of how high up and things they are. We've got when the current meteor showers are on, and sort of various bits and pieces, as well as a calendar of the astro stuff. So just if you just used our website, then hopefully you'd find a lot of information about how to go. If you wanted to look from your desktop about things, then there are applications. So we've got one here, which is called Solar System Scope, and this allows you to whiz round our particular solar system and sort of see what's there. So we whiz in here, and we've expanded the size of the planets here, but it's a lot of fun, and it shows you things like why is Venus showing up the crescent shape at the moment? Where would I find Jupiter and Mars? Why is that in the morning sky versus why is something in the evening sky? You can see all of that there. And it's got some pretty nifty little graphics, so that's not a bad thing to get. But there's a whole host now. So there's applications for your phone where you can find out what the current phase of the moon are. Depends whether you're on Android or whether you're using iPhones. And there's similar things available which go into not just what the moon's doing, but they'll also show you, if you set the date, what planets are doing as well. So there you go. So I can't really recommend any of these because there are just quite so many of them. They all do pretty much a similar thing. So there's enough there that the freeware versions, they usually have a free version and a buy-in. You can try them out and see which ones you like. But if you can find ones with a red screen option, and most of them should do, then that's a very good thing for short usage whilst you're actually observing. But be aware that your eyes won't be as good, even with a red screen on these, as if you hadn't actually looked at them. But it's best to know what you're looking at rather than not know what you're looking at. So sometimes it's best to sacrifice 5-10 minutes to get the information and then have another look. So what else? I showed you Clear Outside as a weather program, a web page. It's also got its own app. So you can take that around with you to find out what the particular weather is like for your particular location, whether there's lots of cloud, what time it gets dark, what the moon's doing. So there's loads of tools that you can use. The one I would recommend, though, is, if you haven't got anything else, is something called Sky Portal. It's a program that's free, I believe, both for Android and iOS. And it is a free version of something called Sky Safari, which is a very good app. And it's got a red screen and it's got compass mode. So you can set that, move the phone around, and it'll show you where you're looking up in the sky. So a very useful app there to find your way around, but be aware again that your eyesight won't be as good for 5 or 10 minutes after using even a red light app as if you hadn't used the app at all, or if you'd used a pure red light and looked in a book. That would be a better way of doing it. Okay, but actually if I take a book out, it'll get wet, and this phone is waterproof, so perhaps I'll just go for the phone. And the other benefit of the phone is you can also use it for other things. So you can, we've got a question from Harry. What is this app? Which one were you? The last one is something called Sky Portal. Yeah, it's called Sky Portal. So if you just did on your app store, Sky Portal, if that's the one you're talking about. Okay, so the other thing you do is take photos. So you can get a mount for telescope, or you can just hold it up behind your binoculars, in this case a monocular, or on the back of a telescope, and have a look through there. And you can get some quite reasonable images from doing that, especially of bright things. So Venus and the moon. So we did a transit of Mercury event in Bath last year, and people got lots of reasonable photos looking through using camera phones. Now, I think I've got some examples of what it is like to hold, but some of these are slightly cheats because to take some of these photos, you actually had to go into the professional settings on the phone to do them. So this is the Flame Nebula, and you had to do long exposure, and this actually required on the back of a telescope with so in the professional mode for long exposure, and it was sort of clamped onto the telescope. So you can do these kind of things. So just as an idea. So star clusters as well. Okay. And these last ones are actually done with a digital single lens reflex camera as well. But again, just you can buy the clamp that goes on the back of the telescope. And if someone else has got a telescope, just buy the little clamp that allows you to put it on their telescope, and you just bring along your camera. But you can get some pretty shots. Here's M51, which is the Whirlpool Nebula, which is in Cannes-Venatici, which is just below the Plough, and quite an easy thing to find, although whenever I'm trying to show it to people, I can never seem to find it, but I think that's just my luck. Okay, that's what I wanted to cover off. A little over, well, 15 minutes over, so apologies for taking the additional time. What questions do you have? Sort of like hopefully just whiz through, just give you a little flavor, but the idea is to give you a flavor, so you want to ask more questions, and so it may provoke some more questions, whether it provokes them now or whether it provokes them in the coming days. Then please feel free to ask. Are there any questions?